Today we are pleased to welcome the first speaker, who is Claudia Fevola from Max Planck Institute for Mathematics in the Sciences. We will talk about KP solitons from tropical limits. Okay, Claudia, you can start. You can share your screen. Okay.
Nice. You can see my screen, right?
Yeah.
Okay.
Okay.
So hello, everyone. And thank you, the organizer, for organizing this and giving me the opportunity to tell you about this work, which is a joint work with Daniela Agostini, Jelena Mandelstam, and Bert Swonfels, which is named KP solitons from tropical limits. So the object of study is the so-called KP equation. And this is a partial differential equation that describes the motion of water waves. And here, the function P is a function in 3 variables, x, y, and t, where 2 variables stands as space variables and t is a time variable. And in particular, as I mentioned, this equation describes the motion of water waves as the one in the picture that I'm stealing from Mark Albowitz's website, which are taken in Mexico. And I'm citing here John Russell, who's the physicist who gave birth who started this study of soliton waves, and that describes the day in which he saw for the first time this phenomenon as the happiest day of his life. And the reason why this partial differential equation is interesting for algebraic geometry is that solutions to this equation are linked to algebraic curves. Indeed, so first of all, let me say that we're interested in solution of this form, where the function tau here needs to satisfy this Hirota differential equation. And as I was mentioning, it is possible to construct tau functions starting from an algebraic curve of genus G. And the first ingredient that one needs to construct such a solution is the so-called Riemann theta function. And this is a complex analytic function that depends on 2 parameters. The parameter Z is a complex G-dimensional vector, and B is a G by G matrix, which is called the Riemann matrix. And it's a matrix that one can construct from the curve. And this is symmetric, and we normalize it to have negative definite real part. And so then one can construct a quadratic form from this matrix and the vector B, and a linear form by multiplying the vector C with Z, where the C so the sum is over all integer lattice points, G-dimensional lattice points. And so this theta function is an infinite sum of exponentials. And so how does this connection to algebraic curves arise? So in 1997, Krichever proved that the KP equation has solution of this form, in which now the theta function is given by this Riemann theta function that we just introduced, where we need to parameterize the vector Z in this way, where U, V, and W will be some complex G-dimensional vector. And I forgot to say to please interrupt me anytime you have a question. And so Dubrovin was the first one who started to study the complex vectors which were giving a solution to the KP equation. And he found out that all of these vectors were giving rise to a manifold. And then last year, Agostini, Selig, and Sturmfeld studied in a work called the Dubrovin threefold of an algebraic curve, this variety, this three-dimensional manifold that they named after Dubrovin. And so this variety comprised all the points U, V, and W in a certain weighted projective space, such that then the corresponding theta function that you can build out of this vector gives rise to a solution to the Rota differential equation. And they studied the properties of this variety, and they also give explicit equation for that. So we now want to introduce some new type of solution to the KP equation. And to do that, we need to make a step back to introduce the grasmanian. So the grasmanian is defined starting from V to be a vector space of finite dimension n over a certain field K. And the grasmanian KV is the set of all subspaces of V which have dimension K. And in particular, just as a notation, we write GRKN anytime that the vector space is just K to the n. And so the grasmanian was born with the idea of generalizing the construction of the projective space. And so in particular for K equal 1, the first example is just the n-1 dimensional space, projective space. And then for K equal 2, for example, we have all the lines, all the two-dimensional subspaces passing by the origin. And what is nice about the grasmanian is that this is actually a manifold, a variety. And so to say that, we need to fix a basis E1, En into our vector space. And we notice that anytime that we have K linearly independent vectors in V, we can write them inside as like rows of a matrix. And so to the matrix M, we associate the subspace V generated by V1, Vn. And we can actually describe a map that to each k-dimensional subspace of V associate all the maximal minors of this matrix. So all k by k minors of this matrix. And this map is well defined since the image of a subspace does not depend on the choice of the basis. And in particular, this map is an embedding. And the image of this map is what is called the grasmanian. And this inclusion, it's actually called the Plucker embedding. And yeah, so one can prove that the grasmanian is a projective variety. And the set, this set where we denote by P with these sub-indices, the minor corresponding to the columns the I1 up to IK in the matrix. So the set of all of these minors is called the Plucker coordinates of the element W in the grasmanian. And so, which are these like special solution, different solution to the KP equation that we want to introduce, and why these are related to the grasmanian? So we fix two natural numbers, k and n, with k to be smaller than n, and a vector of parameters kappa, kappa1, that we name kappa1 up to kappa n, of real parameters. And we can define a tau function in this way. So the difference here is that we don't have any more, as in the Riemann theta function, an infinite sum of exponential, but now the sum become finite. And sorry. And in particular, here we sum over all possible subsets of k elements into the set of natural numbers from 1 to n. And the motivation for this comes from these following results. So Sato proved that a tau function of this form is a solution to the Rotas equation if and only if the point pi is a point in the Grassmannian. So anytime that we take a vector of Plucker coordinates and we construct such a tau function from this vector, we get a solution to the KP equation, and the vice versa also holds. And in particular, any tau function of this shape will be called a Kn soliton. And the solution that we build out of this tau function will be called a Soliton solution to the KP equation. So our main idea was to study the solution to the KP equation, which were now arising from curves defined over a non-Archimedean field, meaning that we define the curve to depend on a parameter. So you can think as a curve defined over such a field as a family of curves that depend on a parameter epsilon. And what happens is that we start from a smooth, nice curve where when t is non-zero, and when t goes to 0, this curve, we can see some singularities arise. And what is nice is that one can also study the combinatorics of the intersection and of the singularities of such a curve. But so the idea was that for the smooth curve, when t is non-zero, we know that we can construct a solution using the Riemann theta function, which is an infinite sum of exponentials, while the Riemann theta function for such a curve becomes a finite sum of exponentials. So this makes us think that this can be a Soliton solution. And this is actually what happens. So let's understand, first of all, why the theta function degenerates to a finite sum of exponentials. So let X be a smooth curve defined over the field K of genus G. And as I mentioned before, the curve for T equal to 0 can be represented by a graph that can be combinatorially described. And in particular, this is described by what is called the dual graph. And the one in the picture is the dual graph for a genus 2 hyperelliptic curve. And the reason why this is called a dual graph is that there is a duality between the vertices and the edges and the components of the curve. In particular, each vertex corresponds to a component of the curve, and then we have an edge between two vertices anytime that two components intersect, and then we have a loop at a vertex anytime that the component has a node. And so, for example, this is the graph for corresponding to two components with the node that intersect in one point. And what we want to do now is to define the Riemann matrix for such a degeneration of a curve. And to do that, we need to fix an orientation of the graph, and it is possible to compute the first cohomology group of such a graph. And this will be a free abelian group of rank G, and thence we can compute a basis of such a group. And if we call E the number of edges of the graph, we can define the matrix lambda to be the G by E matrix, where in each row we record the coordinates of gamma I, so of an element in a basis with respect to the standard basis of Z to the E. And then the Riemann matrix of the graph will be given by the product of lambda times delta times lambda transposed, where lambda is a diagonal E by E matrix that records the edge length of the dual graph. And now we see an example that I hope will clarify all this construction. So suppose X to be a genus 2 curve defined by this polynomial. Well, now the polynomial f of X will depend also on the parameter epsilon. And the corresponding metric graph is a graph of genus 2. And this is given in this case by this picture. And from this graph, we can read off the tropical Riemann matrix Q. And so this is the lambda matrix that we defined before. And then we have this matrix in which we have a 2 for each edge length of the matrix. And so in this case, this is the Riemann matrix. So what happens is that now we look at a family of Riemann matrix in which R of epsilon is a G by G symmetric matrix whose entries are complex analytic function that depends on epsilon and that converge as epsilon goes to 0. And now we fix a point, a real G-dimensional vector, and we consider this shift of the variable z. And this is the way in which the function will look like in this case. And so what we want is that for epsilon that goes to 0, we want this first term to converge. And this is the same as asking that this inequality holds for all lattice points. And so to do that, we take A to be in the Voronoi cell of Q, which means that A needs to verify this inequality. So for example, if we take the matrix induced by Q, which is just the identity matrix, this will be the Voronoi cell. And we can pick a point on the Voronoi cell and define this set, meaning all the lattice points on which the equality holds. And so what happens is that this term converges to 1 anytime that we take one of these 4 points, and it goes to 0 in all the other cases. So this function for epsilon that goes to 0 basically becomes just this finite sum of exponentials, where now the sum runs over all the points in this set that here we're just calling C. And this is an example. So as in the picture before, I was saying that the set C, which is called the Delaunay set, is given by 4 points. And the associated theta function in this case becomes just the sum of 4 exponentials, where the first one is 1. And so we want to do, I mentioned at the beginning that like all solutions that arise from an algebraic curve were parameterized by the Dubrovin threefold. And now we want to construct an analogous of this variety for our type of theta function. So this is just like a recap of what we have seen before. And we consider the theta function now arising from this finite sum of exponential. And we define the iota variety to be the variety of all points A, which are the coefficients in the theta function, U, V, and W in this product space, such that the corresponding tau function that we can construct satisfies the iota differential equation and then will give us a solution to the KP equation. And we have a nice combinatorial way to describe the solution, the equation of this variety. And to do that, we need to introduce a polynomial that will play a main role in this description. So the iota differential equation can be written also in terms of differential operators in this way, where P is this polynomial in the variables x, y, and t. And this also has a physical meaning, and it is known as Solitons dispersion relation. And for any two indices k and l in our set C, so M is the number of elements in C, and so for any two indices from 1 to M, we define pKl to be the polynomial P evaluated in this point, and this gives us an hypersurface in this weighted projective space. And the thing is that just by looking at this set C2, so for each point in C2, you can construct an equation that will give you at the end, like all the equation of the iota variety. And this set C2 is given by all the possible sums of distinct elements in the Delaunay set C. In particular, we say that a point D in C2 is uniquely attained if there exists just one pair KL such that this the element in C2 is attained. And in this case, we say that KL is a unique pair. And in this theorem, we describe the polynomials generating the iota variety. And so we have this polynomial pKl anytime that we have a unique pair, KL, and by polynomials of this shape where we sum over all the indices that give us the element L. So depending on how many times the element D in C2 is attained, we get sums, we get as many sums in this polynomial. And in particular, in the case in which the set, the Delaunay set is a simplex, all points in C2 are uniquely attained, and HC will be defined then just by n choose 2 quartics of this first shape. And so this is an example. So we go back to the case in which the genus is equal to 2, and the set C, in this case, is the square as before. Then the set C2 is given by 5 distinct elements in which all of them are uniquely attained, except for one which is attained in 2 distinct ways. So the elements uniquely attained will contribute with these 2 polynomials, while the point, the polynomial corresponding to D will be this following. And any of these points can also be written as a 2-4 soliton. So it can also be described in terms of the corresponding point in the grasmanian. And so in this case, this is a point in the grasmanian 2-4, and in particular is given by this matrix. So another interesting approach for constructing solution was introduced by Sato And it is, and to describe it, we need to introduce the set of grasmanian. And this setting is interesting to us because it is entirely algebraic, and that's allow us to make symbolic computations. And so to describe the set of grasmanian basically is like an infinite version of the grasmanian. And to describe it, we need to take B to be the field of formal Laurent series. And we consider the projection pi that takes a Laurent series and takes it and brings it into its principal part. And the points in the set of grasmanian correspond to the subspaces U in V, such that the dimension of the kernel of the map pi restricted to U is the same as the dimension of the kernel of the map pi restricted to U, and both of these are finite. And so one question is, so we saw before that for the grasmanian, we could represent a point as a matrix. And now the question is, how do we represent a point in the set of grasmanian? And so any point in the set of grasmanian now is given by an infinite basis, but each of these bases can be expanded in the corresponding Laurent series. And we just like shift all the coefficients by 1, and we take the coefficients in this Laurent series to be the columns in our matrix. So this is, for example, the way a matrix corresponding to a point in the set of grasmanian looks like. And in particular, a subspace U of V gives a point in the set of grasmanian if and only if the matrix has this precise shape, meaning that there exists an L, so from a certain point, one just gets ones on the diagonal, and all zeros above and all possibly non-zero elements below these ones. And this matrix is infinite, like on the left side and also like vertically. So now we wonder, how can we associate a solution to the KP equation starting from a point in the set of grasmanian? And to do this, we need to introduce some combinatorial objects. So we define a Maya diagram to be an infinite sequence of integers, which are all in decreasing order, and such that from some point on, each mi becomes just equal to minus I. And each Maya diagram can be bijectively sent into a partition. And because of the shape of the matrix, it is possible to define the determinant, this determinant, in which basically, so we can denote it by using the partition or the corresponding Maya diagram, but basically the Maya diagram is telling you which rows of the matrix you need to select. And because of the fact that we've seen that the matrix from some point on has just ones on the diagonal and zeros above, this determinant actually makes sense. And so we can associate to each point in the set of grasmanian a tau function. And this is given by this expression where we sum over all possible partitions, and the sigma lambda are the so-called surpolynomials associated to the partition lambda, and these are some complete homogeneous symmetric polynomials. And so this is a function which is like basically an infinite sum in infinite variables. And a theorem by Sato says that like a tau function of this shape is a solution to the KP hierarchy, and conversely, any solution of the KP hierarchy has this form, where the KP hierarchy is just like a generalization to infinitely many equations in infinitely many variables of the KP equation. So one of our goals was to understand the relation between these two tau functions that we defined. So the relation between Soliton solutions, where we have a finite sum of exponentials, and this tau function, which is infinite. And we find out that each kn soliton can be expanded into Schur polynomials. And like what one needs to do is, first of all, to allow non-zero elements just on the first 3 elements of the partitions, and then the C lambda will be some coefficients expressed in this way. And yeah, I'm skipping some details, but the idea is that the first one can be expanded into the second one. And also for such solution, it is possible to construct tau functions starting from an algebraic curve. And so we take X to be a smooth projective curve of genus G defined over a certain field, and we fix a divisor D of degree G minus 1 on such a curve and a point P on it. And for any time that M is smaller than N, we have a sequence of inclusion of these Riemann spaces in which basically we are allowing, for example, in this case, we're allowing to the functions over X to have poles of order at most M at P. And here we're not putting like any limit on P. And we take Z to be a local coordinate on X, and M to be the order of D at P. And we can send, and we have this inclusion given by the multiplication by Z to the M plus 1. And this result by Segal and Wilson says that the image of this space into V is a point in the Sato-Grasmanian. And now we know that like any time that we have a point in the Sato-Grasmanian, we can build a solution to the KP equation. So from a curve, we can construct a point in the Sato-Grasmanian, and this will give us a solution. So this is the case, for example, of a curve of genus 2, and a hyperelliptic curve of genus 2. And so suppose, for example, the curve is given by this polynomial where the lambda 1 up to lambda 6 are just distinct roots of this polynomial. And we take P to be one of the 2 preimages of the point at infinity under the double cover given by the hyperelliptic curve. And we take Z to be a local coordinate around P given by 1 over X. And in this notation now, Y, so this polynomial can be also written, so expanded in this way, where the alpha I will be polynomials depending on the lambda i's. We can then consider 3 types of divisor. And so we want to build an element in the Sato-Grasmanian. So we need an infinite basis from that will give us this point. And so this is the way one can construct a basis. So once we know these functions, we can see that each of these, this set of functions will give us a basis of a point in the Grasmanian. In particular, the set corresponding to these functions will give us a basis that for the first divisor. And if we add the function h1, we get the basis for the other divisor, and so on. But yeah, most of it is that we used this method for implement a method in we used this construction for implementing a method in Maple that taking a curve, an hyperelliptic curve, and a divisor on it, give us a tau function. But of course, since we can't compute like an infinite sum as the tau function defined by Isato, we have like a truncated version of this function where n here will be the order of precision. And if you want to check it out, you can find it on this website. And this is all I wanted to say. And thank you for your attention.
Thank you, Claudia, for the nice talk. Are there any questions?